Hi, I'm Wise and I'll be doing the static analysis for the malware. So the first tool I'll be using is PEiD. This is to identify whether the malware is packed and also the compiler. As you can see, the compiler is using C# code and it's a .NET assembly, and the EP section is .text, and something suspicious is the FF25, which could mean that it is packed, as this is a jump address, and also the entry point is deep within the .text, which is a sign which is not typical for .NET applications. Going through the entropy checks and the EP check and the fast check, we can see that the malware may be packed for entropy, not packed for EP check, and also it says it's packed for the fast check. So all these results differ, probably because the malware uses evasion techniques, and we'll be diving deeper to find out more. To confirm that our malware is packed, we'll be using the strings command line to look for obfuscated strings, and now we can see that there is very obviously many non-human readable strings which show signs of obfuscation and that the malware is packed. Since the malware is confirmed to be packed, we can now open this in Exeinfo PE, which will give us information on how to deobfuscate it. So we can see here that it's using Exeinfo .NET v3.3 to obfuscate the malware, and to unpack it, we use the tool de for dot. To use the de for dot tool, we will first open it up in our tools folder. So the command that we will be using is de for .exe followed by the name of the malware, then -o, which outputs our file into the specified file name after. We'll be calling it NanoCore clean.exe. It has detected the Exeinfuscated.NET 3.3 as shown in our previous section and cleaned the malware and saved it to the new clean file. Now that the malware has been deobfuscated, I'll be using the strings command to look through the strings again of the clean malware file, and we can now see that there's no more non-human readable strings as seen before. So this means that the deobfuscation worked, and since there's so many strings, I'll be looking at the strings from my document. So in the document, there's the NanoCore, which is a certain malware family identified, and a host-based client.exe, some registry functions as seen from Dependency Walker before, 3 registry keys, 1 for persistence on startup, 1 for defense evasion, and 1 for victim fingerprinting, and also a client.log file, and these are all host-based indicators. There's also 2 more files identified, which are host-based indicators, and also scheduled tasks being created, which most likely maintains persistence for the malware. There's also network-based indicators such as connections established, which could potentially be connections to a C2 server. There's also writing server settings after that to a settings.backup file, which could be storing certain information about the C2 server or the behaviors of the malware. There's also another host-based indicator, plugin cache.exe, which is a host-based indicator. There's also another host-based indicator of mutex being created so that the malware doesn't run more than once on a single host. Network-based indicator about the local host and some connection host with a connection port, which most likely tries to connect from the infected host through a certain port to the C2 server. There's also 2 potentially interesting strings, but their purpose are not known as of now. And also lastly, the mscore.dll, which is the file that the malware imports its functions from. Next, I'll be using Dependency Walker to look at the imports and the different DLL files. So the first suspicious DLL file that we're looking through is kernel 32. So it contains functions such as create file mapping, create file w, create mutex w. Scrolling down, there's find first file w. So it shows a lot of file manipulation. And scrolling down, we also see stuff like map view of file. We see more things such as reading the file, sleepx, which is probably used for execution delays, and also there is the write file. So this shows a lot of file manipulation. It could be creating files. Then next we have the advanced API, which shows a lot of registry functions And the important ones are the enum key x, enum value, open key xw, and the query value xw. So this shows registry manipulation, and from URL1, this function creates a blocking type stream object from a URL and downloads the data from the internet. When the data is downloaded, this client application can read it by using the iStreamRead method. So this is most likely exfiltrating data through the internet. Moving on to advanced static analysis, I'll be using dnSpy. So looking at the resources, we can see client loader form which has only 180 bytes. So this means that the malware most likely loads the rest of the payloads from another source. Going to the entry point, we can see the main function, and there's also this client loader form. This looks like an obfuscation method which is used for multi-loaders. So as you can see at the end, there is a class A.s method 0, which looks like this is the initialization chain. So with the initialization chain, we can go into each function and see what it does. So for S method 13, here is doing some payload initialization. For S method 17, it's empty, which is probably just a rabbit hole. S method 20 looks like it's doing some debugging. S22 does some sleep, thread.sleep, which probably does some execution delays to avoid sandboxes and tools. S method 21 creates a mutex so that the malware is prevented from anti-duplication. S method 2 seems like it is the initialization phase of the malware. S method 11 is maintaining persistence using this registry key which auto starts on startup. S method 12 starts an initialization queue for every .dat file in a directory and initializes the exception queue. So the rest of the methods here didn't really look very interesting except for S method 44, which has a connection. So diving deeper, we can look at what are the parameters put into 0 and 1, which is actually 9033 and localhost. So this is probably some connection through the infected host port 9033 to a C2 server.